guided summarization. So, what are target learning and guided summarization? Starting with target learning. So, basically, in target learning, you have a rare class, which are your targets, and a huge unlabeled data set, and you try to get images related to the rare target dataset class in the from the unlabeled dataset, and retrain your model on the those rare classes. And on the other hand, for guided summarization, it's basically when you have to summarize particular data using some user intent, and it could be a query focused or a privacy preserving one, in which in query you focus on that particular aspect, and in privacy you try to avoid uh, that data set, part of data set. So in Prism, they have defined a framework of many submodular functions class, and like they have many functions which balances mainly diversity, representation, and like the similarity and dissimilarity between the target and private sets. And like in the end, they even find that the Prism submodular function generalizes existing methods, and they have superior performance over the existing models in targeted learning and guided summarization. And mainly the existing submodule subset selection had one basic problem, that it did not use the user intent and had only generic subset selection. And even for targeted learning, it could not efficiently get the rare class datasets from the unlabeled datasets. And to solve this, so the previous work which I discussed are mainly like badge and cluster, and for the summarization one, earlier we were using DPP. And to have trade-offs between all of these, they have these submodular functions. So these three submodular functions, in the first one, conditional gain. So conditional gain is for getting the dissimilarity between a set from a private set. And similarly, in the mutual information one, you are getting how a set is similar to a query set. And then combining both these two, we can get a mutual information, like a conditional mutual information, in which you combine the relevance of the query set and see how similar it is from the private set. And building on these, they have three main functions, and the mainly they are log determinant, in which the results show that they mainly capture the query relevance part, and they are taking the log determinant of the similarity matrix they are computing, and the facility location, which is mainly for query coverage. And the graph cut is like a bit in between of these two, which balances both the diversity and representativeness through graph-based modeling. So these are the function for the MI, which is a mutual information, in which you have to get a particular subset related to the query present. And so here, as you can see, there is a FLVMI, FLQMI. The main difference between these are, instead of going over all the data set, like V is the ground set, you basically get the pairwise similarity between the data points and the query set. So it's basically a smaller kernel as compared to the FLVMI1, and the GC is the graph cut, and the log determinant one. And COM is a concave over modular function, in which the psi present here is a concave function. And yeah, so Sij is basically a cross similarity matrix between A and Q's, where Q is our query set and A is the subset which we are selecting. The lambda parameter, like like in other, we are trying to maximize something, and here we just have a like an average summation on the similarity matrix. uh, basically in the graph cut one, they are trying to see how many edges there. So they model all the data set as a graph, and they see how many edges the subset is cutting from the other data set, and like basically get that as a diminishing gain return. So it mainly has two terms like Sij minus lambda and the summation of Sij. Uh, and that is the f function, and they have used it in the mi function which I showed earlier. Yeah, the fa. Hmm. So here we are getting the cross similarity between the A, which is the selected subset, and the query set, and like we are getting the summation of it, and like Mhm. Like between A to A and Q to Q type. Hmm. Right. They have included the second part for the conditional gain part, in which you have to preserve the like to remove the private set. Huh. Uh, in this, like it will remain constant overall optimization rates, because the set is only the A set is changing and not the overall similarity. It's a set similarity of A only. Set that you're selecting is set similarity. Okay. Not even constant. That is the rule. Okay. What do you think about it? Okay. Why is that disappearing? Is there something special? How is it getting merged? And yeah, similarly, these are the functions for the CG and CMI. There is no function of graph cut for CMI part, and and yeah, so the methodology that they incorporate for the target learning one is like the goal was to improve model performance on rare classes and using minimal labeling effort. So they basically define a CMI function using here T is the target set and P is the private set, and you optimize this graph cut or like a log determinant function to get a optimal subset out of the unlabeled data set, and then you label the selected subset and then retrain your model with the rare class. And for the guided summarization one, there are three types of summarization you can perform. One is a query focus, in which you only focus on the query, and similarly there's a privacy preserving one, in which you just avoid data related to the private set, and then you can combine these both using the CMI functions defined before to balance both the query focus and privacy preserving part. So for results, they mainly have used data sets like CIFART and MNIST, and this SVHN and PMNIST. And for guided summarization, there was a image collection data set, which was like which had a human as a like summarizer as ground. So in targeted learning, they showed around 20 to 30% accuracy gain over existing baselines, and baselines like badge and cluster, and overall around 12% accuracy on all the classes. And even the labeling efficiency was around 20 to 50 times more efficient than random sampling, and around 4 times more than the existing baselines. And they also have proposed a mixture model of a prism mix, in which they have combined all these graph cut and all the facility location and log determinant to get a mixed model, and that outperforms all the baselines and all of them individually as a function. So yeah, in this graph of the results, the A part, as you can see, the highest accuracy is for the uh, purple line, which is for FLVMI. And similarly, these are for different data sets, the A, B, C, D one. And then in E and F, we are seeing how many data points it gets out of the unlabeled data set. So as you increase the size of the labeled set size, the targeted sample also increases for the like graph fit one as compared to the uh, other baselines. And yeah, then they have compared the condition. So if we are having both the conditional mutual information versus mutual information, like the functions are different, but if you remove just the privacy part, then is it giving the same results for both CMI and MI? And in the end, they have given the overall gain. So like earlier, these graphs are only for the rare class on the targeted gain, and the PM list is overall gain achieved by these submodular functions. And so yeah, in conclusion, the Prism uses various submodular functions uh, to have a guided subset selections, and it like even generalizes the state of the art results like badge and cluster. So and even grad match, and like in future work we could include like right now we are using only one modality as images in here to get the similarity matrix, but in future we can have multiple domains like text and images to get the multimodal cross selection of the dataset.
So now let's move to the second paper, Orient, submodular mutual information measures for data subject selection under distribution shift. This paper was published in Europe's 2022. So starting with the introduction, as for machine learning models, we need a huge data, and for our target domain, we don't have those data available, so we use closely related domains, data from closely related domains, but this leads to suboptimal performance on our target domain which we want to. So we need to perform a domain adaptation and to address the problem of this distribution shift created, and this is called supervised domain adaptation when we have the labeled datasets. So key contributions of this paper is the technique Orient, which is a SMI based submodular mutual information based subset selection framework, and it is inspired from three existing techniques like CRAG, cluster, and grad match, and we will see the effectiveness of this as compared to these techniques also. So the goal of Orient is we have a reference data set, the target domain, and we have some images, suppose, from that domain. And also we have a large source data set, and we want a smaller subset of this source domain, which is large. And we want a domain subset such that the mutual information between the reference data set and this subset is maximized so that we can we can use it for training our machine learning model and have an efficient performance. So how do we accomplish the subset selection is we have the reference images and we have the whole domain dataset. Given a instance of our training in a machine learning model, we have the parameters. So we compute the gradients of the reference images as well as the source domain dataset, and we compute the cosine similarity, and we choose the subset A such that the mutual information is maximized using this similarity. So we the to represent those data images, we use their gradients on the current model. Yeah, yeah, the model this is adaptive. So the while we are training, we are having the current parameters, and we use that parameters and the weights to compute the gradient at that instant. And after every L epochs, like we won't know that how much the current model has learned by using the reference model. Yeah. So it is effectively treating as we are separately calculated the subset using that reference model. So the algorithm is like we start from an instant of the model and we have the target data, source data, and subset, random subset A. We start from it and we perform L epochs so that we have new parameters and weights. And we use these parameters to compute the gradients, and then we compute the similarity and perform a subset selection, and use that new subset A to perform another L epochs. So if we have to perform total E epochs, we perform this process E by L times to get the final model, train model on dynamic subsets. So this is the pseudocode for the same. Coming to the results, as like for results, they have chosen a 30% subset. So we expect 3 times speed up. And they have also marked a green cross, which we can see as random. So they have chosen a 30% random subset. And of course, that should be that should have a less accuracy than the full set, which is red circle. So we wanted a technique so that our accuracy doesn't drop, but we have a speed up of 3. And we can see that most of the Orient techniques, in most of the cases, all the 6 graphs, we have achieved that. The accuracy is similar to the full model, and we have achieved the 3 times speed up. So in conclusion, it is evident that this proposed approach Orient is achieving comparable performance. And also the main limitation of their work is that although it reduces the training time, but to compute the similarity and store it in memory, we require a large memory. So that's a limitation of this. Yeah, which have less parameters so that we can have similarity, but we need to have some interdependency between both those models so that we know that the master model is learning. Yeah. Yeah, we have it.
Yeah. Mm.
Yeah, we have it.
So now I'll be presenting a paper on understanding contrastive learning using the distributionally robust optimization, and this paper was published in Neurips 2023. So introduction, contrastive learning is basically a kind of self-supervised learning which has been used for representation learning in various kind of domain like image, language processing and graph-based tasks. But there are some issues that exist in this. The first one is a sampling bias in a in negative samples, which affects the learning effectiveness. And second issue that occurs is because of over conservatism or sensitivity of contrastive learning to outliers. So basically, they are trying to first of all theorize the contrastive learning, trying to understand what contrastive learning is doing through using the distributionally robust optimization algorithm. And it also asks two of the key questions like why does is the contrastive learning is tolerant to sampling bias, and what role does a temperature parameter tau that comes in the loss function of contrastive learning, what interpretation we can have from it. So first of all, talking about contrastive learning. So it is basically a type of learning which encourages similarity between the positive samples and tries to separate negative samples. And it uses the info NC loss, which is given as follows. And it has a temperature parameter which we can fine tune. So like some of the terms like Px is the origin sample distribution, P naught is the positive samples from the distribution, and Q naught is the negative sample distribution. And some of the key terms that they will be using is the phi divergence, which is basically kind of divergence used to define quantified difference between various probability distribution, and it is a mix of KL divergence and a chi-square divergence, which ensures flexible way to model uncertainty in contrastive learning. And they have also used eta, which is basically a robust radius, and which is used to define an uncertainty set around a baseline negative sampling distribution. So a larger value of theta would allow us more deviation from the negative sampling distribution Q naught, making the model robust to any kind of distribution shift in that. Yes, sir. Yes, sir. Yeah. That is also contrast learning. Yes, sir. Yes, sir. They do. Hard learning negatives, basically it's kind of there can be some type of negative samples which are similar to the positive one. So in that, what we do is we particularly use that those samples to try to discriminate the model, so better it can better learn any kind of that hard negative samples. Yeah, discretized version of that. Yeah. So now talking about the distributionally robust optimization algorithm. So basically it tries to define the worst case loss objective and tries to minimize it over the potential distribution. So what we take is we try to find a uncertainty t set Q and try to like define a loss function based and maximize the estimation on that, and the fire divergence, and we try to like have a bound on the fire divergence between that uncertainty set and the negative sample distribution set which we have, and that bound is given by the eta. So like it tries to maximization problem for the even the worst case distribution which is over the Q naught, and then this kind of like over a loop it updates the model parameters using HDD, and then we can also adjust the temperature parameters and all things to control, and eta to control the size of the uncertainty set. And this is repeated until convergence or until we have ensured robustness in the distribution shifts. So in this paper, they have tried to like prove that the contrastive learning is basically a kind of distributionally robust optimizations on negative samples, which kind of makes it robust to the bias sampling. Now, also talking about the role of sorry, sir, can you repeat? Yes, sir. Actually, in kind of hard negative sampling, we can adjust like the eta, so the uncertainty set we choose. So it can be like if in case of hard negative sample, so the divergence we want should be lesser for them. So we can adjust that for hard negative sampling kind of thing. Here we can like eta we can control, so we can control that. Yes, sir. Mm-hmm. Yes, sir. Hmm. Yes, sir. That is kind of the algorithm is doing. Yes, sir. Yes, sir. So like the role of the temperature coefficient tau. So basically the formula is given as in the below the slide. So a large tau would be would mean a smaller robustness radius, and we have seen that a smaller robustness radius would lead to like a smaller variance from the distribution, or would allow for a lesser distribution shift. So it can potentially mislead to negative ideal negative distributions, and a smaller tau would mean a better robustness to the distribution shifts, but can lead to have variance penalty. So we would have to select an optimal tau for that. So for experimentation, they have used various data sets. Like for vision tasks, they've used CIFAR and STL, and for NLP tasks, they have used STS, and for graph-based tasks, they have used TU data sets. And the findings they've after performing the experiments, the finding were as follows. So tuning the temperature parameter tau, we can significantly improve our performance, and like the contrastive learning can match some of the explicitly designed techniques to handle sampling bias, and we can also like use both tau and eta to basically kind of control variance control and the hard negative mining or those kind of situations. So yeah, but so basically there are two kind of limitations and drawbacks of this contrastive learning. So it is too conservative. So either we can set those parameters so it either over focuses on hard negatives, and sensitivity to outliers is basically if there's some kind of outliers, it assigns them abruptly high weights, so it causes instability in training. So to mitigate that, they have like proposed a adjusted version of the previous loss, which is the ADNEC loss, in which what they are doing is for the worst case scenarios or worst case distribution, they are kind of giving them Gaussian like weights to refine them and to improve the training stability. And so like the like assigning those Gaussian like weights would won't for outliers and for hard negative samples, they won't give abruptly high weights to them. So yeah, and the results were as follows. It performed on the multiple domains, it performed better than the info NEC, and it also improves the convergence speed, and on all the domains it performed better. So like on the image contrasted learning, we can see that there are for Cefartin, the top one accuracy is shown. So the red one is a ADNEC graph, which performs better than tau naught, tau star, or the alpha CL direct. These are methods. Basically, tau naught is the in which is a method in which they like fix the tau to 0.5. Tau star is a method in which they optimally choose tau through a fine grid search method, and similarly for alpha CL direct method. And similarly for NLP tasks, is the sentence embedding performance, and the for graph tasks we can see that the ADNEC performs better, not better, if not better than second most better than most of the models that are present. Yeah, so concluding our slides, so the key insights were so the contrastive learning is basically performing. We have seen how contrastive learning is used through the DRO on negative samples, and it also plays a fundamental role in robustness, and the ADNEC laws they have proposed tries to mitigate the weakness of contrastive learning and improves generalization. So yeah, now